All right, so this first example says a computer company makes desktop and laptop computer factories in 3 states, California, Texas, and New York. The California factory produces 40% of the company's computers. The Texas factory makes 25%, and the remaining 35% are manufactured in New York. Of the computers made in California, 75% are laptops. Of those made in Texas and New York, 70% and 50% respectively are laptops. All computers are first shipped to a distribution center before being sent out to stores. Suppose we select a computer at random from the distribution center. So, first thing we're going to do, we're going to draw a tree diagram to help us see the actual situation. And we're going to find the probability that there is a laptop. So a tree diagram, you start with, honestly, this part doesn't really matter. For example, I always say computers because we're looking at computers. But the word that you put here really doesn't matter. I suppose you don't even really need a word. It just needs to think through the situation. So we have a computer company, and they make factories in 3 states, California, Texas, and New York. We make our 3 branches from computers. Some are made in California, some are made in Texas, and some are in New York. It then tells us that California produces 40%, Texas makes 25%, and the remaining 35% are manufactured in New York. So on our branches, we're going to put our percents, so 0.4, 0.25, and then 0.35. So we can see that 40% from California, 25% Texas, and 35% in New York. It goes on to tell us at each of the sites what laptops, and they make desktops and laptops. So from each state, we're going to have branches for laptops and desktops. Tells us that in California, 75% of laptops, by the way, L stands for laptop, D is desktop. So if 75% of the computers made in California are laptops, that means 25% are desktops. Then it tells us those made in Texas and New York, percent and 50% respectively are laptops. So Texas makes 80% laptops, which means 30% are desktops. And then we have 50% for New York, so 50% laptops and 50% desktops. And then at the very end, of our tree, we're going to take the number on the branches and multiply together so that we find the probability that a computer made in California is a laptop, computer made in California is a desktop, Texas laptop, Texas desktop, New York laptop, New York desktop. So you have branches from each of those. And to find those numbers, you just multiply the two numbers. So 0.4 times 0.75, pretty sure it's 0.3, but it's a Friday, so I'm going to check. Yeah, 0.3. And then for California desktop, 4 times 0.5 should be 0.1. Texas, 0.25 times 0.7 for laptops, which is 0.175. 0.25 times 0.3, 0.075. 0.35 times 0.5, 0.75, and the bottom one is the same because it's so 0.35 times 0.5. Now, if I make a diagram, my end numbers should add to 1. If I made a mistake somewhere, it's going to end up giving me a value than 1 or greater than 1. So it's kind of a nice little build check that if I add numbers together, I get 1. I made my tree diagram correct. So that is our tree diagram for the we have the computer company, the computers in California and in New York, each factory, laptops and desktops. So we were able to set up a tree diagram so that we can answer probability question. Find the probability that the computer is a laptop. So we're asked to find the probability the computer is a laptop. It doesn't specify that it comes from California or Texas or New York. We're going to look at all the laptop probabilities. So a California laptop, a Texas laptop, and then a laptop. And we're going to add those three together to find the probability that our computer is a laptop. So 0.3 chance it's a laptop in California, 0.175 chance it's a laptop in Texas, and 0.175% chance, I said that wrong, 0.175, not percent after that, chance that it was a laptop made in New York. 3 plus 0.175 plus 0.175 is, excuse me, 0.65. No? Alright, this next one is just another tree diagram. If we were in person, you guys do this one on your own, but I can't really walk around and check your work. So you guys get to watch me do another one. And every year I pick on a kid to pick on who tends to always be late. Some of you may know Chloe Rose. She's usually pretty late. We've had to have people call her up from nap time to make it to my class. So I picked on her. So it says Chloe Rose hits the snooze bar on 1 o'clock on 60% of school days. If she doesn't hit the snooze bar, there's a 0.90 probability that she makes it to class on time. However, if she hits the snooze bar, there is only a 0.70 probability that she makes it to class on time. On a randomly chosen day, what is the that Chloe is late for class. So, and this is where, like I said, a person would be creating your own tree diagram to help you out here. And this is where all sorts of words at the beginning, so it really doesn't matter what you put. I've had kids put the person's name, Chloe. I've had kids put alarm clock. That's why up at the top I said it doesn't really matter what that first word is. I've even had kids not put a word in, they just start their branches. I'm going to say alarm clock because two branches are hitting the snooze bar and not hitting the snooze bar. So snooze and no snooze. And it tells us that it's snooze 60% is, so that's 0.6. Means that she does snooze 40%, so 0.6. And then from snooze and no snooze, there are two options. She is either late or she's on time. So late, on time. Late, on time. Tells us that if she's in snooze bar, so I'm down here at no snooze, there is a 9-0 probability she makes it on time. So this one is 9, she's on time. Which means this is 0.1. It then says if it hits the snooze bar, there's only a 0.0 probability she makes it to class on time, which means that this would be 0.3. And then we're going to put our last branches that give us probabilities for the different options. Misplaced my calculator. All right, so snooze and late, 0.6 times 0.3, 0.18. Snooze and on time is 0.6 times 7, so 0.42. No snooze and late, 0.4 times 0.1, which is 0.04. Snooze, excuse me, and on time, 0.4 times 0.9, which is 0.36. And then a quick check to make sure that they add to 1. Oops, that's 2 zeros. So they do add 1, so I know that I'm on the right track. And I kind of hit a question in there. It says, on a randomly chosen, what's the probability Chloe is late for class? So that would be hitting snooze and being late, plus not hitting snooze but still being late. Probability that she is late. Let's see, where do I want to write it? Didn't leave my room. I'll put it up here. Comes from 0.18 plus 0.04. Would be 0.22. So Chloe would be late 22% of school days. And then in my horrible proofreading, I forgot to change last year's name down. Last year I picked on Aiden. It should still say. So suppose that Chloe is late for school. What's the probability that she hit the bar that morning? So this is a conditional probability of what we learned yesterday. So this question, we know that Chloe is late. That's our given condition. And if she's late, the probability she hits snooze. So snooze, given she was late. So hopefully yesterday you remember that we learned our condition probability rule that says P of B given A is equal to P of A and B divided by P of A. So for this one, on top we would have the probability she's late and she hit snooze. Divided by the given condition, which is late, so the probability she was late and hitting snooze. Here's snooze, here's late, so here's the probability of being late and hitting snooze, or snooze and late, or where you want to put it. So 20 on top. And then the probability she's late, that's what we did up here, so we're going to divide by 0.22. 0.18. So 0.8181, 8181, 8181. Any questions on that one? Alrighty. Oops. Alright, so on this one, it says 55 high school students participate in a school athletic team at some level, and about 5% of those athletes go on to play on a college team in the NCAA. We're going to come up with our general multiplication rule. But we need to answer what percent of high school students play a sport in high school and go on to play a sport in the NCAA. So we're given two pieces of information. We're told 55% of high school students participate on a team. They play a sport in high school. So I'm going to say H high school means play a sport in high school. That's going to be one of my events. It then tells us that 5% of those athletes go on to play on a college team in the NCAA. So NCAA is going to be my other event, play a, well, we play on an NCAA team. So the first phrase I underlined just tells us the probability that a student plays a sport in high school. So the probability that a kid plays a sport in high school is 0.22. 5. The other underline says 5% of these athletes go on to play on a college in the NCAA. 5% of these athletes, meaning athletes who played in high school. So that last phrase that I underlined is actually a conditional probability. They're saying that the probability a kid plays on a NCAA team, given they were on a high school team, is 0.05. The question that we need to answer is, what percent of high school students play in high school and go on in the NCAA? So we want to know what's the probability of high school and NCAA. So we have the 3 parts of our conditional probability rule. Let's see, where do I want to write it? I think I'm going to put it down here. So yesterday we talked about the probability of B given A comes from the probability of A and B divided by the probability of A. Today, we know the conditional probability and the probability of the condition, and we need to find this guy here. That's the missing piece we need today. So we can use some algebra skills to rearrange that formula so that it's solved in terms of the probability of A and B. And that would be done by just multiplying sides by the probability of A, so that we get our fraction to be gone. And I multiply by the probability of A. Parts cancel out, so the probability of A times the probability of B given A is equal to the probability of A and B. And that is what is known as our general multiplication rule. So if we find the probability of A and B occurring, we can find it by taking the probability of A times the probability of B given A. And you can also find it and B could be found by the probability of B times the probability A given B happened. So just notice that if you have a conditional probability, if you multiply it by the probability of the given, you can find the probability of A and B happening, which is what our diagram was doing for us. So we had the probability of A, the computer being made in California, times the probability of computer being a laptop, knowing it was made in California. And so we were finding our general multiplication rule with our tree diagram. This is what it looks like using the probability notation. To answer the question, play in high school and play in NCAA, we would take the probability played in high school multiply it by the probability they're on an NCAA team, given they played in high school. The two pieces of information that the problem gave us. So we would take 0.55 and multiply it by 0.05. .55 times 0.05, which is 0.0275. If you're a high school athlete, the probability that you go play a sport in college at an NCAA school, not one of the other conferences, is less than 3%. Anybody go to an NCAA school? Is yours an NCAA school? Or is it NAIA?
Mine's a D3. Yeah, it's NCAA.
Well, look at that. Sophie's one of the 3%. Taylor, are you playing soccer in college?
Yeah, I'm going to ACU.
Where?
It's in Abilene. Where my parents went to school.
Oh, okay. I feel like you told me that last year.
Yeah.
I'm sorry, I forgot. Chance, are you playing in college? Chance, leave on me.
Hopefully.
Say that again?
Hopefully.
You're echoing on me. Is Tanner going to do any sport in college?
Yeah, he's going to Alabama.
Really? You're just messing with me.
Chance is just besting you, Mrs. Little.
He's just messing with me?
Yeah, he's just besting.
Okay. Anybody else know that's an athlete going to play in college? Cody, are you playing baseball in college? Cody's not listening to me. All right. Any questions before I move to our next one? Nope. Alrighty. So this time we're going to talk about tennis. Tennis great Roger Federer. Sorry if you're a tennis person and I butchered that. Made 63% of his first serves in the 2000 season. When Federer made his first serve, 78% of the points. When he missed his first serve and serve again, he won only 57% of the points. What's the probability that he makes his first serve and wins the point? So, you could put his, I'm gonna say serve. So he either makes his serve, make means it stays in, miss means it goes out of bounds. So, let's see. He makes it 63%. Oh man, I gotta do 7. I don't know why the 3s and the 7s really mess with me. So 7 would be 70, so this is 37. And then the other part is winning the point. So he wins the point, doesn't win the point. I'm gonna say the point. I don't think in tennis if they don't point, they lose the point, but you guys get the idea. Does anybody really understand how to keep score in tennis? They've got
Unfortunately, yes.
They have such weird. They have like love and like they're and count by like points. Don't you like get 15 points or something?
Yeah, it's so ridiculous. Like, they just use words arbitrarily. Like, literally, like, some people, like, after you score, some people will say and some people will say 5. Like, it doesn't even matter. It's like,
Why not just count by ones?
because tennis, I don't know. I'm sorry, any tennis players in the class.
I know, right? I have never understood how they keep score, but I know they have words, but okay. So if he makes his first serve, he won 78% of the points. So then, oops, 8. I was doing mental math, sorry. So would put us at 80, so this is 22. And then he missed the first serve and had to serve. He won only 57% of the points. So 3 put us at 60, so 4. And then we're going to put our last branches, so 0.63 times 0.78, 0.4914, 0.63 times 0.22, 0.386, 0.37, not 34, 0.57 is 0.209, and then 0.7 times 0.43, 1591, 0.4914, 136 plus 0.21. So I added my 4 numbers on, so I know I'm on the right. Question asks us, what's the probability that he makes his first serve and wins the point? So probability serve is made and wins the point. So that would look at tree diagram. He made the point, or made the serve, and wins the point. So we would have our answer right. If you think about it in terms of our general multiplication rule up here. Sorry, I'm trying to make sure I can show both things at once, but I can't zoom out any further. All right, so the probability of A and B, probability of A times probability of B given A. So what our tree diagram really is telling us is the probability that he made the first serve times the probability he won the point given he made the serve. So he made the serve was 0.63. When the point given he made the serve, so when given he made the serve was 0.78, and we would get our 0.4914. So a tree diagram is doing the general multiplication rule for you. But you make the tree diagram back, but to just use the general multiplication rule because you were given the 2 pieces of information you needed. Are there questions that you guys have for me? Alrighty, well that is it for today.